the effects of gas entrapment below the phreatic surface on groundwater dynamics. So we're shifting a little bit in scale. However, we are going to remain in this river dam applications. The work I'm going to present was worked with my colleagues Oliver Stelzer and Bernhard Odenwald, who will work with the German Federal Institute for Waterways Engineering. So, some hint how this could. I can try. Okay. Thank you. So this is the one. So to start, we must start with a question. So it's generally accepted that below the phreatic zone we have full saturation. However, if we look inside, we will see that there are some little bubbles, and these bubbles can be due to groundwater level fluctuations, or they can be due to organic processes occurring there. So if we look at the saturation distribution, so we have here the phreatic surface, here we have the capillary curve that was presented by the former talk, and we can assume that we have here some kind of distribution. So very, very little bubbles of gas, but they can have an impact on groundwater dynamics, as I can show you. And if you understand these processes, it will help you to interpret some field measurements or laboratory measurements, which I will present later on. So if we have here some gas bubbles entrapped herein, so when I'm talking about the scale of a pore scale, these gas bubbles can, due to the composability of gas, they will enhance our storage properties. So the assumption of our storage of our groundwater is going to be different than we thought if we would assume a complete saturation. And we are not the first one to find that out. It was about 50 years ago. There were some analysis in Scotland where they installed some pressure transducers in a dam, and they observed the pressure time series after the water level was lowered. So, and we have here K conductivity in the dam of about 10 to the minus 8 meters per second. And the drawdown was about 30 centimeters per hour, so not too fast. However, we have to consider the value of the change in head to the hydraulic conductivity. And this was quite a high value. And please remind of this parameter, hydraulic conductivity and the velocity of head change, because it plays a role. So the people who recorded this were Peyton and Sample, and this is what they observed. They observed this is the head distribution they had, and this is what they would have expected. And what do we see here? We see here some banded head lines. And these banded lines, they indicate some hydraulic gradients. And you can see we have here hydraulic gradients. And if you look at it, there are hydraulic gradients from the inside of the core to the outside. And this is what they would have expected. So they would have not expected any gradients. And as we know from the other talk, is these hydraulic gradients can be critical. They can lead to erosion processes in this kind of materials. These guys, they assumed that gas bubbles was the reason for this. The amount of air present in the pores in a bank fill affect the pore pressure-strain relationship. At that time, this factor is not readily assessed by laboratory tests of theory. 50 years later, we can say we have an idea of what was happening here. So what is the motivation? The place I work with, we are doing a lot with bank protection. And we have these ships going over here, and these ships, they create waves. And these waves represent quite a rapid change in head at the shoreline. So we can have, within 12 seconds, we can have a change of 80 or 90 centimeters. And of course, we are interested in the gradients that are could be induced by these rapid changes, because these gradients determine the depth of a protection, of a bank protection. So this is relevant for us. If we carry out some soil experiments, we fill sand, and then we have a certain head, and then we carry a head drop at the top of about 50 centimeters. And if we have installed some pressure transducers in the middle of that sand column, what we see is this kind of time series. So there is a delay. There is a delay in head. And this is not exactly what we would have predicted with a groundwater model, because if we assume there is no gas in there, I have very, very small storage properties. So we would have expected a rapid drawdown, a simultaneous drawdown of all the measured heads, but we have not. And this is the reason why we get some head differences from inside to outside. So the propagation is retarded, and the explanation for this retardation is the compressibility of the bubbles. So we know that flow process always coupled. So we have deformation and flow are always coupled. And if you read the book of Hans Dirsch, you will find this. And of course, this gives quite a complicated equation. So the hydrogeologists looked for ways to decouple the flow from deformation. And we can do that. So, and I don't want to go too much into details into these equations, but if you do so, if we assume this is the deformation, if we assume that the material we work with, the groundwater, if it is not deformable, then we can get rid of lots of equations. So you have to consider that we always assume a rigid matrix. This is a storage term due to the compressibility of the solids. This is of course very, very small, we can forget about that. And then we get these two storage terms and this flux term. And these two storage terms, they open a possibility to represent the process I'm talking about. So this storage term, it represents the compressibility of the water, and this represents the storage change with pressure. So there are two ways to consider this. One way would be to say, okay, we have complete saturation, then this would vanish. And then we would have to consider the compressibility of a gas-water mixture. This is a very simple approach. The other approach would be to say, okay, we have here a water compressibility. This is very, very low, so I can forget about this term, and I must consider this saturation change with pressure. And if you look at this is very similar to the Richards equation that was presented in the talk before. So the idea was, perhaps we can apply the Richards equation, we just have to extend the saturation pressure relationship just below the phreatic surface. And this is what you can do if you have some idea of what is the distribution of saturation with pressure. Then you just can extend this and just handle the whole thing as unsaturated. Another more simple approach would be to assume some kind of a linear relationship. And we know that the C, which is the water capacity term in the Richards equation, this would be just a constant. So these are the two approaches. If we choose the first approach, you can see that we can have we have to assume some kind of initial saturation. This is the parameter S0. And this is a parameter we can hardly measure in the field, but it determines the amount of gas below the phreatic surface. However, we can check that, and if we look at this, we made some kind of an inverse problem approach. We set this up to 98, and setting this up to 98, we got almost the identical pressure distribution, head distribution, as Benton and Seppel did 50 years ago. However, if we do not consider this effect, we have exactly the distribution the thought should be right. So this is quite a good indication that we can have a very, very small amount of gas can be responsible for such banded lines of potential head. So here you can have the head histories. So this is what was measured. The bold line is the process of the watering of the water level, and only when we consider the gas entrapment we can simulate, we can predict what they had really observed. So we carry out some dimensional analysis to look for this, and to make the whole thing very simple, we regarded a one-dimensional problem, and we know that the domain geometry is one parameter which is important there. I told you the drawdown rate is very important in comparison to the hydraulic conductivity, and there is also some kind of compressibility contrast which will play a role, and I will tell you about that in a moment. It is there is a parameter, it's called the Scampton B parameter, which is well known in geotechnical engineering, and this Scampton B parameter is a good dimensionless parameter to consider the difference between the stiffness of the soil, so this is the compressibility of the soil, and the compressibility of the soil and the fluid. So, and if you look at this term, this is the sum of the compressibility of the soil plus and the compressibility of the gas water system. So this is what this parameter we know already. It's the specific storage parameter which we know from groundwater flow. So this parameter goes from 0 to 1, and it represents, if it's 0, then you have a rigid soil and a compressible fluid, and if it's 1, you can have a compressible soil and an incompressible fluid. So I can show you what comes out from parameter analysis with this canonical example. So we have an excavation pit, and this excavation pit is filled with water, and I'm going to dewater the pit, and I will going to see what's happening here at this point. This is information which is important to design the depth of this sheet pile wall. And here I assumed quite a large amount of gas, about 10% saturation, and we have a soil that is incompressible, so a rigid soil, and I just varied the V to K value, and as it was expected, the faster the lowering of the water is, the higher you will get an excess pressure. So what we see here is the pressure compared to the steady state case. So, and the smaller the dewatering occurs, the lesser is this effect. So normally these kind of computations that are made on the steady state, and the steady state would reveal no pressure, no excess pressure at all there. And this, if you have this kind of occluded bubbles there, then you are good advised to make an analysis, a transient analysis, because otherwise you wouldn't find these peaks. So here now we are making some changing the compressibility contrast, and we find out that the largest excess pressure appears when we assume that the soil is rigid. And this is also quite logical. If the soil is rigid, then excess pressure builds up. But if the soil can deform itself, then the pressure is decreased. So the excess pressure is related to the stiffness of the soil. So, as I told you, this is good for the bind protection design. Just to show you in a very extreme case what can happen. If you do not consider this gas entrapment, you would come with this kind of potential distribution. However, if you have gas there, then you come out with this kind of potential distribution, so you would have here some gradients, and the question arises whether slope stability might be endangered there. So I did a finite element porous elastic analysis, and at the end, unfortunately at the end, I found that Carlson and Jäger, they found in the 50s an analytical solution for this problem. However, their problem was related to heat conduction. However, at the level of the differential equation, it described exactly the problem that we have of flow and deformation. This is a coupled problem. So my model was all ready, and I could validate it with an analytical solution. And what we have here is the one-dimensional pressure distribution over depth for this. And what you can see here is that as long as the V to K value is low, then you will not have to expect any problems. And probably a V to K value of 10, this might be in 90% of all the groundwater problems. You are lower than that, so you won't expect no problems. However, if the V to K value rises, so if we have a very, very fast change of head, and this can occur especially with soils of low conductivity, then you will have more pronounced excess pore pressure. And here you can see the effect of the compressibility contrast. So B0 corresponds to a soil that is rigid. So this corresponds to the pressure that a groundwater model would predict. And if your soil is not so rigid, if your soil gets more compressible, then the B value increases. And as I told you, if the soil can deform, then the pressure declines. So my recommendation to people who have found that this could be an issue for their analysis would be first to estimate the V to K value. If you are below 10, forget about the thing, this thing has no relevance. However, if you are above, if you are in such a region and you should consider this excess pore pressure, then you can estimate the bulk modulus of the soil. You have to estimate some kind of initial initial saturation for gas entrapment. So 2-5% could be. We have not such an idea about field cases. You have to estimate the pressure which would apply in your case, and from that you can compute some compressibility for the water and gas phase, and this you can transform into a specific storage coefficient. Then you can perform the analysis with your FEFLOW model, and you would come here on this on this branch, which is some kind of a conservative estimate for your expected excess pore pressures. So I want to thank you for your attention.